Hello, my name is Kell Geisler, and today we're going to be learning about our non-steady state mass flow. And for the example we're learning about today, what we're going to be doing is we're going to start off with our example. So we're just going to have a tank here, and it's going to be filled with water in this example. And down here, this is going to be our cross-sectional area, and the height of the water, we're just going to name that as H. And since we're dealing with mass flows, steady state, non-steady state mass flows, we're going to have a flow in. We're going to have a flow in, we're going to name that Q in. And then we're also going to have a flow out. And we're going to name that Q out. And our flow out is going to be defined by, is going to be equal to alpha, a constant alpha times h to the 1/2. That's how we're going to define that. And just to start, we're going to have an initial temperature of 300 Kelvin and Ti, sorry, initial temperature. And also, this temperature reference is going to be 320 Kelvin. Our flow rate in, we're going to start with our given 1 cubic meters per second, and we're going to start with an initial height of 1 meter and a cross-sectional area of 1 meter cubed. And we also need our temperature going out. And this is just going to be the temperature of the system. And this is also going to be our T going in. That's going to be our 320 Kelvin. And what we need to do now is, in the future, we're going to be plotting this. We're going to be plotting the temperature as well as the height over time with our equations. And what we're going to do is we're going to set up an equation so that we can do that. And so what we're going to start with is going to be, it's going to be the change in the mass of our system, and we're going to set that equal to the change in the mass going in minus the change of the mass going out. And the way we're going to determine this is we're going to use our values to, as well as density to input into these equations, into these values. So what this is going to turn into is the change in the density times the cross-sectional area times our height, our h up here, and that's going to be equal to the density going in, the density times our flow going in minus the density times our flow going out, which is alpha times our h to the 1/2. And what we want to do is we want to take this with respect to time. So we're going to say dt down here, little t for time, because we have big T for temperature. And we are going to take out our densities because they can all cancel here. So what we're going to be left with is d, or we can also take out this h, or this a, because it's just value, so it won't be changing. So a times dh over dt is going to be equal to the flow rate going in minus our alpha times our h to the 1/2. And we can divide all this by A. We divide all that by A and get our first equation, dH dt is equal to the flow rate going in minus our alpha h to the 1/2 all over A. And this is going to be our first equation right here. After we found this equation, we need to now make the same equation, but with our enthalpy and our energy. So the energies, our kinetic energy and our potential energy, those are going to cancel out, and we're not going to worry about those just right now. So we're just going to make an equation just like this, and we're going to say the change in the mass of our system times the internal energy of our system is going to be equal to the enthalpy coming in times the change in the mass in, minus the enthalpy going out times the change in our mass going out. And now we have to take this with respect to time. And we're going to say dt, dt, and dt. So we're taking respect for time. And what we can do now is input our values. So instead of the mass of our system, we're going to do the same thing. We're going to say d times the density times A times H all over dt is going to be equal to the enthalpy in times the change in our mass coming in, which is going to again be the density times the Q in minus the enthalpy out times our T going out, which is going to be our alpha h to the 1/2 times our density as well. And now we can take all these densities out, cancel, 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 cancel. And what we're left with is again our A dH dt equals enthalpy in times the flow rate in minus enthalpy out times alpha h to the 1/2. And you divide by A again as well. Now here we might look a little stuck, but we need to replace our U's and our enthalpies. So we need to replace the internal energy of our systems and our enthalpies. Oh, so we also need to include the U's down here of our system. So these U's are going to stay here. So we look a little stuck, but what we need to do is we need to say that the change in our enthalpy is going to be equal to the specific heat times our change in time. And then our change in U is going to be equal to the heat capacity times our change in time. And we're also going to work with the equation to exchange our U's, which is going to be the U of our temperature minus the U reference is going to be equal to the heat capacity times T minus T reference, our reference temperature. And now all we need to do is start plugging these in and replacing. So we're going to say D, the change, times our cross-sectional area, times H, and then we replace that U, the internal energy of the system. We replace that that internal energy with the heat capacity times T minus T reference, and all of that is going to be over the change in time. And now we replace our enthalpies. And so we're going to say that the enthalpies are going to be replaced also by CV times T minus T reference, and then include our flow going in minus our specific, or our heat capacity times T minus T reference times, I'll just write it right down here, it's still part of this equation, but it's going to be times our alpha H to the 1/2. So this is going to be times that. And this is replacing our enthalpies as well as the internal energy of our system here. Actually, these are not the heat capacity. This is the specific heat, because in this equation, our the change in our internal energy, this U, or sorry, the change in our enthalpy here is replaced by the specific heat, and our change in internal energy here is replaced by the heat capacity. So these both need to be the specific heat. And this we can simplify down. What we're looking for in getting is we're looking to get the change in temperature over time. So we're looking for dt d big T over d little t. And so what we need to do is we can take out these reference T's as well as the heat capacity and the specific heat. And I'll show you how to do that in just a second. We just need to, this is going to give us the change in, at least A on the outside, change in H times our T, because our heat capacity is going to be equal to our specific heat. So those can cancel, as well as the T references out, over our change in time. And we can say that it's going to be equal to the flow rate in times our temperature minus our alpha H to the 1/2, also times our temperature. We can divide our area, and we can separate our height and our temperature, and we get our A has been divided, and we get our height times our change in temperature over time plus our temperature times our change in height over time. And so what we need to do is subtract, we need to get this change in temperature over our change in time. So we're going to subtract this T dH dt and divide this H over this side, which is going to leave us with, so equals everything that's over here, the flow rate in, T times the flow rate in minus T times our alpha, H, height to the 1/2, all divided by A, minus that T times the change in height over time, and then all of this times 1 over H, that gets rid of this, as well as this height. So we were just left with the change in temperature over time equals the temperature times the flow rate in minus the temperature times alpha, our height to the 1/2, all divided by our cross-sectional area, minus the temperature times the change in height over time, times 1 over the height. And this is going to be our next equation that we're going to use. Oops. This is going to be our next equation that we're going to use. And we're going to use this equation to code and find a graph with the temperature and the height over time. Now we are going to make these graphs. We're going to code in Python. We're in Colab right now. And we're going to make these graphs of change in temperature over time and change in the height of our system over time. And so we're going to graph these. So we started with our import numpy as np, and we've imported our IVP, to our solve IVP, and then we've said plotly subplots and make subplots so that we can plot our values. And we've started with our cross-sectional area, and that is going to be in meters squared, as well as our initial height, that's going to be in meters, 1 meter, and our initial temperature, that's going to be in, that's going to be in Kelvin. That's going to be in Kelvin. Our initial temperature, our temperature going in is also going to be in Kelvin, 320 Kelvin. Our flow rate is going to be meters cubed per second. Our alpha is just our constant value, and then our time is going to be in seconds. And these are all the values we've been given from the drawing at the top of the whiteboard. And now we're going to start plotting this. So we're going to use ODE. We're going to say def ODE, then we're going to say TK, I believe. And we're going to say HT equals our K. And now we're just going to input our equations that we found earlier. And those are going to be the change in our enthalpy equal to, I believe, flow rate in minus our alpha times our enthalpy to the 1/2, times our height to the 1/2, I believe. Sorry, this is height, my bad. It's a change in height. Times flow rate in minus our alpha times our height to the 1/2, which we found earlier, divided by our A, we know that. And then we're going to do our change in temperature. And that is going to be our temperature in times our flow rate in minus our temperature times alpha, times our height to the 1/2, 0.5 as well. Then divide by A again. minus our temperature times change in height, all divided by our h, all divided by our height, so like 1 over height. And we're going to return our array. We're going to make this an array so we can graph it of change in height and change in temperature. And that should give us what we need to get started. Just want to make sure there's no issues so far. Let's just say restart and run. Yes. Okay, we're good, good, good. Perfect. Now we are going to add code and solve this IVP to start. And we're going to say SOL equals solve our IVP times our ODE, and we're going to make this 0 times our time, or our 0 and our time in the array, and we're going to denote this array, and we're going to say NP dot array parentheses our height, our initial height, and our initial temperature. Temperature. And we're going to say after this, our method is going to be DAU redo, and since output is, we're going to say true, and that should end our parenthesis there. Are we good? Is that the right parenthesis? Yes, that is the right parenthesis. .sol, and then we're going to enter again, and we're going to start our t-plot, plot over time. Oops. Is going to be equal to np space. We're going to start with 0, and then we're going to say our time 300 Kelvin. We're going to say our height temperature equals SOL. We plot that SOL, that IVP that we just made. And now let's just plot it up. Add some more code. Should be good. Yes. Okay. Let's run it. Just make sure. Oh, we got an error. Name plot is not defined. Oh, this should be tplot. Yes. Okay. Now it's good. Perfect. And then we say fig. We're going to plot our equations. Make our subplots, and this is going to start in row 1. Whoops. This is going to start in row 1, and column calls equals 2. And we're going to say fig dot add scatter. Add our scatter plot, and that's going to be our x equals our t plot from up here. And then our y is going to be equal to our height. And then row, this is going to be row 1, column 1. And we're going to do the same thing down here, but we're just going to change our y. It's not going to be height anymore, it's going to be t. And instead of column 1, it's going to be in column 2, I believe. Yes, that should be good. Fig, make subplots, rows 1, columns 2, add scatter. We got our t-plot as our x. Our y is going to be our height in our first graph, and then our second graph, our y is going to be our temperature. And it's going to be in column 2, so we can make 2 separate graphs. And let's just see how this works. Let's restart run. Okay, this looks correct. This looks like exactly what we need for our change in height over time. That looks great. But this change in temperature over time looks a little bit off. So let's just look and see if we might have made just a small mistake. Up here. Oh, looks like we didn't. That's supposed to be to the 1/2, not times 1/2. Let's see if that fixes it. This is better. Okay, this is exactly what we were looking for. So this is our plot of our height over time, and then this is the plot of our temperature in Kelvin over time, and this is changing in meters. Now we're going to look over back on the board. We're going to go look into concentrations. Now we're going to be working with concentrations. And with concentrations, we're going to be replacing our temperatures with concentrations of a solute instead. And so instead of our temperature in, we're going to have our solute flowing in. That's going to be our C in, and it's going to be 1 kilogram per meter cubed. And and then this C, the C initial is just going to be 0.1 kilograms per meter cubed. And we're changing that here. Everything else, the cross-sectional area, the height, the flow rate in, and the flow rate out all stay the same. That's why we can continue with this equation here. And we can say that the change in the mass of the system is going to be equal to the change in the mass coming in minus the change in the mass going out. Same equation. All with respect to T. All with respect to T. And then do the same thing we did here. But what we can do now is we can say that we have a new density, but this doesn't matter because we can say the density of the system is going to be equal to the density in is going to be equal to the density out, flowing out. All these are going to be equal, so the density does not factor in, the new density does not factor in to what we need to do. So now because these densities are all the same, we can use this. We don't have to rederive this equation. And so all we have to do is take this, and instead of our temperatures, what we need to use is our concentrations. So with this, we can say that the change in mass of the system is going to be the change in the area times the height times C all over the change in time. And that's going to be equal to our flow rate in, or actually, I'll start with C. That's going to be equal to our concentration in times our flow rate in minus this C, this initial C, this 0.1, that initial C times our flow rate out. And as we know from last time we derived this, our flow rate out is just our alpha times height to the 1/2. Okay? And so we have this. And we want it to look something a little bit like this because we're using the same equations and we're just replacing the T's for our C's. So you go through the same process. You can take out this A. You can take out this A. Take that out. Divide it over here. Okay? And then we can change this to our H times our the change in concentration over the change in time plus our our concentration times the change in height over the change in time. And this is going to equal exactly what we had up here, but it's going to be easier for us. All we have to do now is just subtract this over here and divide by our h again, same thing, and we can get our new equation that is going to be just like this, but for concentration. And that's going to end up giving us our change in concentration over change in time is going to be equal to, same thing as down here, our concentration in times our flow rate in minus our concentration, our initial concentration, times that alpha, times the height to the 1/2, all over A minus our concentration times our dH over dt, concentration, change in height over change in time, just like we did down here. And then we just need to divide by this h, 1 over h. Or you could divide the whole thing by h. Either way, this is what we're going to use for our second equation. We're going to stay with this equation because remember our densities are all going to be the same, so it doesn't mess with this equation. And so we derived the same exact way we did the last one, and we find this. And this is going to be very, very similar, as we're going to see, to this. And our concentrations now are changing. So we're going to see our concentration over time versus our height over time. We're going to see how that changes, and we're going to be able to code that in Python. Okay, now we are back in Python, and all we're going to do is we have both of those equations. We have our temperature equation here, and this is going to stay almost the same. We're just going to replace our temperature with our concentration, and we're going to input our new values for our concentrations. So our initial concentration, it's not 300 Kelvin anymore. It is 0.1, and it's going to be kilograms per cubic meter. And our temperature coming in is going to be our concentration coming in, and that is just going to be 1 kilogram per cubic meter. Oops. Per cubic meter. Everything else is going to stay the same. Our cross-sectional area, 1 meter squared. Our initial height, 1 meter. Concentrations are changed. Our initial flow rate stays the same, 1 meter cubed per second, cubic meter per second. Alpha stays the same, and we're still going to do this over a time span of 100 seconds. And now we have our ODE, and our T and K are going to stay the same, but we're going to change this T to our concentration, still going to equal K. Our change in height stays the same, but our change in temperature turns to change in concentration. Our temperature in changes to concentration in. Our T times alpha turns to concentration times alpha times the height to the 1/2 minus the concentration times the change in height over 1 over height, or divided by height, same thing. And our array goes from change in height, change in temperature to change in height, change in concentration. And we're solving here, still stay with the same time. Our temperature initial turns to concentration initial. Same. Time stays the same. Here, T plot. Our height and temperature turns again to height and concentration. And subplots are going to stay the same. T plot, change in height, and then our Y It's going to be equal height in the first one, and then concentration in the second one. And this should be good. Unless I'm missing something, I should be all right. Let's say restart and run all. Let's see what we get. Hopefully we didn't miss anything. Okay, and good. This looks perfect. So this is, again, our height in meters over time. Same graph. Our height, very similar graph, stays the same. And then our concentration, this will be in kilograms per cubic meter. This is how it's changing. Very similar graphs. Same equation, very, very similar graphs. And that is going to be it for our non-steady state flow examples and the height over time versus our temperature over time, as well as our height over time versus our a new concentration of a solute over time. Thank you very much.